Good day, everyone. So this is our first week for the subject Logic Design and Switching. And for today's discussion, we're going to discuss number systems. And for our objective, so we're going to convert different number systems, perform addition of signed and unsigned binary numbers, and represent decimal numbers in binary code. So in this first module, we will review number systems, particularly decimal, binary, octal, and hexadecimal. We shall also dive into binary arithmetic, complements, and touch a little bit on binary codes. But first, we shall define some concepts. Okay, so what is logic circuits? Logic circuits are made up of one or more electronic devices that perform logical operations. These circuits are used for control or processing function in digital system. And as for digital system, so this is made of interrelated components and manipulate discrete elements of information represented in ones and zeros. A computer is an example of a digital system. And we will be employing a lot of abstraction in this course in simplifying things. We sometimes need not bother with things that we don't need, thus hiding them so that complexity can be avoided. So digital system make up of more than one number system. We constantly being seek them throughout the course. So what is a unit? A unit is a single object, for example, an apple, and a number is a symbol that represents a unit or quantity. And the base or radix of a number system signifies the number of symbols used in that system. The base of any system is always expressed in decimal numbers. The radix of the decimal system is 10. So this means that there are 10 symbols used in the system. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So the base of a number system is indicated by the subscript following the value of the number. The highest value symbol in a number system is always 1 less than the base of the system. So in digital system, the most common number system other than the decimal are we have the binary, we have the octal, and we have the hexadecimal. So binary uses two digits, 1 and 0, and they are called binary digits, or they are called bit 1 or bit 0. And as for the octal, octal uses 8 digits, that is 0, 1, 2, 3, 4, 5, 6, and 7. And for hexadecimal, it uses 10 decimal numbers plus the numbers A, B, C, D, E, and F. So A is an equivalent to decimal, which is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So for the number conversion, so we have the decimal to binary. So these are the following steps in converting decimal to binary. Okay, so it involves dividing the decimal number by 2 to give an integer quotient. And the remainder 0 or 1 will be the coefficient of the binary number. So continue dividing the integer quotient until it becomes 0. So write the coefficient in descending subscript order. So we have an example. So for example, okay, so we're going to convert 11 base 10 to binary. And to do that, so we need to get the quotient and the remainder. So let's begin. So 11 divided by 2 is equal to 5, and the remainder is 1. 5 divided by 2 is equal to 2, remainder 1. And we are going to divide the quotient. 2 divided by 2 is equal to 1 with a remainder of 0. And 1 divided by 2 is equal to 0 with a remainder of 1. And we are going to write it in descending order. So we are going to start to write from A3 going to A0. So we have 1 here, and then we have 0, and then we have 1, and then we have 1 here. Let's have another example. So again, given a decimal number, and we're going to convert it to binary. So convert the decimal number 26 base 10 into its binary equivalent. So again, we're going to divide 26, okay, repeatedly by 2. So let's say we have here 26. So 26 divided by 2 is equal to 13 with a remainder of 0. And the quotient of this, again, it will be divided by 2. So 13 divided by 2 is equal to 6 with a remainder of 1. And the quotient of this will be again divided by 2. And that is 6 divided by 2. That will be 3. And 3 is the quotient and have a remainder of 0. Again, we're going to divide 3 by 2. So that is 3 divided by 2. That will be 1 with a remainder of 1. And 1 as the quotient will be again divided by 2. So 1 divided by 2 is 0, remainder 1. And we are going to write it in descending order. So this will become our MSB. So when we say MSB, this will be our leftmost bit. Okay, MSB stands for most significant bit. Again, so this will be our leftmost bit here. And this followed by this one. This one here. On the third here, on this position. And we have this. And we have 0 as our LSB, or the least significant bit. And the least significant bit is our our rightmost bit. Let's have another example. Okay, so convert the decimal number 41 base 10 into its binary equivalent. Again, we're going to divide 41 by 2 repeatedly. So let's say we have 41 divided by 2 is 20. 20 remainder 1. And we're going to divide 20, which is actually the quotient, again by 2. So 20 divided by 2, that is 10, remainder 0. And we have the quotient of this, again, will be divided by 2. So that is 10 divided by 2, that is 5, with a remainder of 0. And the answer of this will be again divide by 2. So 5 divided by 2 is 2, with a remainder of 1. And we have here 2, okay, divided by 2 is 1, with a remainder of 0. And we have 1 divided by 2 is 0 with a remainder of 1. Again. Okay, so this one will be our most significant bit. Again, our most significant bit is the rightmost bit. So this one is our rightmost bit. Okay, followed by 0. Okay, followed by 1. followed by 0. Okay, followed by 0 here. And our LSB, or the least significant bit, that will be our rightmost bit. So again, we're going to write it, okay, so up. And now, let's convert binary to decimal. And the process to convert binary to decimal is what we call weighted multiplication. So we're going to multiply each bit of the binary number by its corresponding weight factor. So we are going to start from bit 0, which is 2 raised to 0 is equal to 1. Bit 1 is 2 raised to 1, that is equal to 2. And bit 2 is 2 raised to 2, or that is equal to 4, etc. And we're going to sum up all the products in step A to get the decimal number. Again, we have 0, 1, 1, 0. And our leftmost bit will start with 2 raised to 0, or that will be equal to 1. Followed by 2 raised to 1, that would be equal to 2. Followed by 2 raised to 2, that is equal to 4. And 2 raised to 3, that is equal to 8. And we are going to get the product of each bit. So for example, we have here 1 multiplied with 0 is equal to 0. And that this is 2. 2 multiplied with 1, that would be equal to 2. And 4 multiplied with 1, that is equal to 4. And 8 multiplied to 0 is equal to 0. And we are going to sum up all the products, that is 0 plus 4 plus 2 plus 0, and that will be equal to 6. Therefore, we can say that 0, 1, 1, 0 base 2 is equal to 6 base. And we have here an example, another example from binary to decimal. So we're going to convert the binary number 10010 into its decimal equivalent. So we have 10010. Again, we're going to start with 1 because this is 2 raised to 0, followed by 2 raised to 1, that is 2, 2 raised to 2, that is 4, and we have here 2 raised to 3, that is 8, and that is 2 raised to 4, or that is equal to 16. And we're going to get the product of each bit. So we'll start from bit 0. So that is 1 times 0, that is 0. That is 2 times 1, that is 2. And that is 4 times 0, that is 0. Or that is 8 times 0, that is 0. And we have here 16 times 1, that is 16. And we are going to sum the all products. So that is 16. And then this is 2, right? 16 plus 2 is 18 base 10. So if you're going to based from your observation, we can actually say that those aligned with 1 and to its corresponding position, for example, we have here 2 and we have here 16. So we just get their sum for us to get the decimal equivalent. Next is we have the number-based conversion from decimal to octal. So it involves dividing the decimal number by 8 to give an integer quotient. The remainder will be coefficient of the binary number and continue dividing the integer quotient until it becomes 0. So write the coefficient in descending subscript order. Okay, so this actually it's almost the same with the binary, decimal to binary, but this time instead of dividing it by 2, we are going to divide it by 8. So let's have an example. So let's say we are going to convert 153 base 10 to octal. So 153, again, divided by 8, that is 19, with a remainder of 1. And we have the quotient 19 will be divided again by 8, and that is equal to 2 with a remainder of 3. And we have a quotient, we're going to divide it again by 8, that is 0 with a remainder of 2. So therefore, okay, we will write this one in descending subscript order from A3 going to A0. So A3 will be our first digit, A1 is the second digit, and 1 will be the second digit. So therefore, 153 base 10 is equal to 231 base 8. So let's have another example. So let's say we have decimal to octal. So we're going to convert the decimal number 189 base 10 into its octal equivalent. So 189 divided by 8, that is 23 with a remainder of 5. And we're going to divide again the quotient by 8. So that will be 23 divided by 8. That would be 2 with a remainder of 7. And again, we have 2 as the quotient. Again, it will be divided by 8. And 2 divided by 8 is 0 with a remainder of 2. And we're going to write this one in a descending subscript order, meaning this will be our MSB, or the most significant bit, or we call this one the rightmost bit. So this will be written first, followed by 7, and 5 to be the last digit. So we have 2, 7, 5. So therefore, 189 base 10 is equal to 275 base 8. So a number-based conversion. So we're going to convert decimal fraction to binary. So the decimal fraction is multiplied to 2 to give an integer and a fraction. So the integer will be the coefficient of the binary number. So the process continues until the fraction becomes 0. So for example, convert 0.6875 base 10 to binary. So first, we're going to multiply this value, 0.6875 times 2, that will be equal to 1 with a fraction of 0.3750. Okay, and we have 0.3750. Again, it will be multiplied by 2. That is, we have 0 with a fraction of 0.7500. And the 0.7500 again will be multiplied by 2. And that is equal to 1 with a fraction of 0.500. And this will be again multiplied by 2. So we will have a product of 1. So hence, we can say that 0.6875 is equal to 1011 base 2. So again, that is 0.1011 base 2. And we are going to write it, okay, from top to bottom. So we have 1011. Okay, so and now, let's convert binary to octal and octal to hexadecimal, vice versa. So because binary, octal, and hexadecimal numbers are all powers of 2, there is a relationship that we can exploit to make conversion easier. As for this example, so let's say we have 101101 base 2. That is also equivalent to 132 base 8, and that is also equivalent to 5a base 16. So to convert directly between binary and octal, group the binary bits into sets of 3. Because, diba, if you can see 2 raised to 3 is equal to 8, so you may need to pad with leading zeros. So as for this example, so we have 1, 0, 1, 1, 0, 1, 0. First, we have to group them by 3. So this is one group, this is another group, and this would be our last group. So we could pad zeros here just to complete the whole sets, okay, or the whole to complete the group. Okay, and let us convert each group into its equivalent decimal. So for example, we have here 0, 1, 0, and if you're going to convert 0, 1, 0 to its decimal equivalent, that is 2, and we have here 0, 1, 1, that is actually equal to 3, and 0, 0, 1 is equal to 1. So therefore, 1, 0, 1, 1, 0, 1, 0 base 2 is equal to 132 base 8. And to convert directly between binary and hexadecimal number, okay, group them, okay, or group the binary bits into sets of 4. So you may need to pad with leading zeros. And as for our example, so we have 0, 1, 0, 1, 1, 0, 1, 0. And we have first, we're going to group them by 4. So the first group is 1, 0, 1, 0. And the other group is 0. Just pad 0 here. 1, 0, 1. Okay, and let us convert them into its equivalent decimal. So we know the first group is 1, 0, 1, 0. And if we're going to convert this one to binary, if we're going to convert this one into decimal, that is equivalent to 10. And 10 is not a valid value for hexadecimal. Actually, 10 is equivalent to A. So we have here A. And we know that 0, 1, 0, 1, if we're going to convert it to decimal, that is 5. So 5A base 16. So again, 0, 1, 0, 1, 1, 0, 1, 0 is equal to 5A base 16. So let us have another example of binary to octal to hexadecimal. So using the shortcut, convert the hexadecimal number A616 to its binary and octal equivalent. So use your calculator to check your answer. So first, convert the hexadecimal into binary by expanding the hexadecimal digit into binary groups of 4. So for example, right? So we know that A is equal to 10. And if we are going to convert 10 into its equivalent binary, that is 1, 0, 1, 0. Again, for 6, we have to convert this one to its equivalent binary. And the binary equivalent of 6 is 0, 1, 1, 0. And let's combine them. So therefore, A6 base 16 is equal to 1, 0, 1, 0, 0, 1, 1, 0 base 2. And if we are going to convert 1, 0, 1, 0, 0, 1, 1, 0 to its equivalent octal, this one, we're going to convert this into octal. So all we have to do is group them by 3, right? So one group, okay, one group will have 3 bits. Okay, so let's start from right, going left. So we have 1, 1, 0 as our first group, 1, 0, 0 to be the second group, and 0, 1, 0 would be the third group. And converting them into its decimal equivalent, so 1, 1, 0 is equal to 6, 1, 0, 0 is equal to 4, and we have 1, 0 that would be equal to 2. So therefore, 1, 0, 1, 0, 0, 1, 1, 0 base 2 is equal to 246 base 8. And as for binary addition, so similar to this decimal addition, if the sum of two numbers cannot be expressed as a single digit, carry 1 into the next column. As for binary addition, so if we have 0 plus 0, that is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and if we have 1 plus 1, that is 0, carry 1. So let's have an example. So let's add 0, 1, 1 base 2 and 0, 1, 0, 1 base 2. So we have here 1 plus 1 is 0, carry 1. 1 plus 1 is 0, right? Carry 1 plus 0 here is 0. So we have 1 plus 1 plus 1 is 1, carry 1. And we have 1 plus 0 plus 0 is 1. So binary overflow, or we have overflow, occurs if the sum does not fit in the available digit. If there is overflow, the leftmost bit or the most significant bit or the MSB is discarded. So let's say we're going to compute a 4-bit sum of 1101 added with 0101. So the fifth bit is discarded. So the final sum is 0010. So let's look at that problem. Okay, so let's say we have here 1 plus 1, that is 0, carry 1. 1 plus 0 is 1. 1 plus 1 is 0, carry 1. And 1 plus 1 plus 0 is 0, carry 1. And we have an overflow. So again, an overflow is discarded. So our final answer is 0010. Okay, and as for the sign and magnitude of numbers, so comparing the most common ways of representing binary number, sign and magnitude will win in terms of human readability. So that is because we are used seeing this representation. So negative numbers are written with minus sign followed by the magnitude. And positive numbers may or may not have a plus sign preceding the magnitude. So the signed binary numbers are written with the MSB signifying the sign. So the rest of the bits are used for the magnitude, and the number is positive if the sign bit is 0 and negative if the sign bit is 1. So again, signed binary numbers are written with the MSB signifying the sign. So if the MSB is 0, so the number is positive. If the MSB is 1, then the number is negative. So 0 is represented in two ways. So we have positive and negative. So if the difficulty to perform ordinary binary addition on signed magnitude numbers, so let's look at this example. So let's say we have 3. So 3, we have positive 3 and we have negative 3. And let's look at, okay, so the equivalent of positive 3 and negative 3 in binary. So if we have here a 4-bit binary, so we have 0 is equivalent to 0011 base 2. That is positive 3. And how about negative 3? So negative 3 base 10 is equivalent to 1011 base 2. And how did that happen? How we got 1011 as an equivalent to negative 3? And the answer there is the 2's complement. So what is 2's complement? So this overcomes the limitation of sign and magnitude number. If the most significant bit is 0, our leftmost bit is equal to 0, then the number is positive. So if MSB is equal to 1, then the number is negative. So it goes through the process taking the 2's complement. So flip the bits and add 1 to the least significant bit position. So this is useful in finding the representation of a negative number and in determining the magnitude of a negative number. So let's have an example. So let's say we have 2 and we wanted 2 to be represented in negative binary number. So again, let's say we would like negative 2 to be represented in negative binary number with the use of 2's complement. So first, okay, so we have 2. First, we have to get or derive the decimal equivalent of 2. So the equivalent of 2 is 0, 0, 1, 0. Okay, so again, that's the first step. Convert it to decimal. And then that's followed by flipping the bits. If it is 1, flip it to 0. And if it is 0, flip it to 1. So for example, here we have 0. Flip it to 1. Okay, so 0. Okay, so flip it to 1. There. And then we have here again 0. Flip it. It will become 1. And then 1. Flip it. It became 0. And 0. Flip it. So 0 became 1. So just flip 0 with 1 and 1 with 0. So the next one is we're going to add 1. Okay, so plus 1. So if we are going to add it, so we have here 1 plus 1 is actually equal to 0, right? And we're going to have, there we have a carry. So 1 plus 0 is 1. And then bring down 1. So we have here 1, 1. So we have 1, 1, 1, 0. That is equivalent to negative. Okay, and let's have an example. So let's say we have negative 5. So let's say we have negative 5. And we wanted to convert negative 5 to its equivalent negative binary number using 2's complement. So again, the first thing that we're going to do is we have to get the equivalent, decimal equivalent of 5. So that is 0, 1, 0, 1. And we have to flip each bit. The second step is we have to flip each bit. So if it's 1, it will become 0. And if it's 0, it will become 1. So we have 1 became 0. 0, it became 1. And 1 became 0. And 0 became 1. And the third step is we're going to add 1. So therefore, negative 5, diba, is equal to, we have here 0 plus 1 is 1. Bring down 1, bring down 0, and bring down 1. And again, negative 5 is equal to 1, 0, 1, 1. That is in 4 bits. Okay, so let's say we have naman negative 13 and we wanted to convert negative 13 into its equivalent positive decimal in 8 bits. So this is in 8 bits. So again, negative 13 is equal to 1, 1, 1, 1, 0, 0, 1, 1. And to convert it back to its original form, which is the positive, okay, so we have, again, flip 1 with 0 and 0 with 1. So 1 will become 0, 1 will become 0, 0 will become 1, 0 will become 1, 1 will become 0, 1 will become 0, 1 will become 0, and 1 will become 0. And you have to add 1. So 0 plus 1 is 1, bring down 0, bring down 1, bring down 1, bring down 0, bring down 0, bring down 0, and bring down 0. And if we are going to convert 1, 1, 0, 1 to its equivalent decimal, okay, that will be equal to 13. And as for the arithmetic, using 2's complement number, so if two numbers are both positive and using ordinary binary addition, so if one number is negative, obtain its 2's complement and proceed with ordinary binary addition. So if both numbers are negative, obtain both 2's complement and proceed with ordinary binary addition. So if the sum is positive, the magnitude is easily obtained. And if the sum is negative, the magnitude is obtained by taking the 2's complement of the sum. Okay, so let's have an example. So let's say we're going to add a positive number with a negative number. Okay, so we have to take the 2's complement of a negative number and use regular binary addition. Okay, so let's say we have 9. So first, we get the binary equivalent of 9 in 8 bits. So that is 0, 0, 0, 1, 0, 0, 1. That is 9. And how about negative 5? For negative 5, we have to get the 2's complement of negative 5. And that is, okay, so again, the 8-bit equivalent of 5 is 0, 0, 0, 0, 1, 0, 1, 0, 1, I'm sorry. Okay, so this is 5. And again, we have to flip each bit. So it will now become 1, 1, 1, 1, 1, 0, 1, 0. And add 1. So 0 plus 1 is 1. Bring down 1. And then bring down the rest of the binary bits. Okay, so we'll have 1, 1, 1, 1, 1, 0, 1, 1. There. Okay, and let's proceed to regular binary addition. So we have 1 plus 1. So we have 1 plus 1 is 1. Right? 1 plus 1 is 0. Right there. It's 0. Carry 1. So 1 plus 0 plus 1 is 0. Carry 1. So 1 plus 0 is 1. 1 plus 1 is 0. Carry 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 1. And 1 plus 1 is 0. Carry 1. And again, since this is 8-bit, we are going to disregard. Okay, we're going to disregard the last bit or the 9th bit. So our answer is 0, 0, 0, 0, 0, 1, 0, 0. And if we're going to convert this one into a decimal, that would be equal. So let's take this example. Let's say we have here a negative number added with positive. Since this is negative 9, again, if we saw negative number, we have to convert them to its negative equivalent in binary by using 2's complement. Okay, so we have negative 9. So again, how to we have to get the 2's complement of 9. So first, we have to get the decimal equivalent, diba, in binary. I mean the binary equivalent. So that is 0, 0, 0, 0, 1, 0, 0, 1. That is 9. Okay, and we have to flip each bit. Okay, so that will become 0, becomes 1, and 1 becomes 0. So we have here 1, 1, 1, 1, 0, 1, 1, 0, and we have to add 1. So this is now the 2's complement of negative 9. Okay, and since 5 is positive, all we have to do is get its equivalent binary. Alright, so we have here 0, 0, 0, 0, 1, 0, 1. And let's add. Okay, so we have here 1 plus 1. Okay, so 1 plus 1 is 0. Carry 1. 1 plus 1 plus 0 is 0. Carry 1. 1 plus 1 plus 1 is 1. Carry 1. 1 plus 0 plus 0 is 1. And then we have here 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1. Okay, so we do that is, since that is the 8th bit or the most significant bit is 1, therefore, again, if it is 1, if our MSB is 1, therefore it is a negative. And to check the answer, get the 2's complement of this one. Okay, so if you get a 4, therefore, your answer is correct. Ayan. Okay, so if we're going to convert it back, diba? So let's say we have here, this is negative 4, right? And let's flip each bit or get the 2's complement by flipping each bit. So 1 becomes 0 and 0 become 1. So we'll have 0, 0, 0, 0, 1, 1. Then add 1. So if we're going to convert this 1, this should be equal to 4. And our answer is correct. Ayan. Okay, so for binary codes, okay, so discrete pieces of information are transformed into what looks like binary numbers, but the meaning is unlike that of ordinary binary numbers, and easily read by human, and use more bits than equivalent binary numbers require a minimum of 4 bits per digit. So we have the binary coded decimal, or known as the 8421. So it uses 10 out of possible 16-bit combination. So both are examples of weighted code. So BCD columns are assigned positive weights. Okay, so we have 8421 and 84 negative 2 negative 1 columns are assigned positive and negative weights. And conversion is similar to how hexadecimal are written, but only up to the equivalent of 9 base 10. So the BCB is simply the 4-bit representation of the decimal digit. For multiple digit base 10 numbers, each symbol is represented by its BCD digit. So what happened to the digits not used? Okay, kasi if we have here 4-bit, so therefore we have 16, right? We have 16, an equivalent of 16 decimal symbols. But in BCD, we just use 10. We have 0 to 9 only. Right? So it's just like now converting it into hex, diba? So this is 001, this is 0010, this is 0011, this is 0100, this is 0101, this is 0110, and 7 is 0111, and 8 is 100, and 9 is 101. Okay, and the question is, what happened to the 6 digits? Okay, and let's look at this example. Let's say we're going to add 3, added with 3, that is 011. If we're going to convert it in decimal, that is 011 added with 011. So our sum is 0110. And if we're going to convert 0110, actually that is 6. And 6 is found on the BCD table. So it is in the range and a BCD digit representation. So what if we have 7 plus 6? And 7 plus 6, that is actually 1101, and this is again out of range. This is out of range. If we're going to convert this one back to its equivalent decimal, this is actually 13. And the 13 is not in the range of the BCD. Kasi in the range of BCD, that is actually from 0 to 9. So we have to add 6. In that case, if the value that you have added is greater than 9, you have to add 6. And when you add 6, okay, so you have to, again, group them by 4, just like this. So we have 10011. So 1 is the carried out of the next BCD digit. So therefore, the final answer is 100. So this would be another digit. This is 1 digit and this is another digit. So the answer is 13 base 10. And as for the gray code, so only 1 bit in the code group changes in going from one number to another. So non-weighted, and it uses the entire combination of 16 bits for 4-bit number. So given, we have here the binary code, and this is the gray code. And how are we going to derive the gray code from a binary code? So first, okay, you write first the most significant bit of the binary code. So for example, let's say we have 3. For example, let's take 011 and convert this one into gray code. So first, okay, so what is the most significant bit of 011? So that is 0. So you write 0. And then the next step is you're going to compare its adjacent bit. Okay, so if the adjacent bit is similar, you write 0. And if it is different, you write 1. So for example, okay, so 0 and 1. Compare 0 and 1. 0 and 1, they are different. The other one is 0 and then the other one is 1. So since they are different, you place 1 here. Okay, 1. Okay, and then you next move. You go to the next adjacent bit. So let's say we have here 1, 1. So we know that 1 and 1, they are similar. Both bits are 1. So again, if both bits are 1, so you place 0. So therefore, the gray code of 3 is 0, 1, 0. So let's have another example. For example, we have 6. So first, what are we going to do? So get the most significant bit. The most significant bit of 110 is 1. So you write 1 there. 1. Okay, so the next step is you compare adjacent bits. So that is 1, 1. So are they similar? So if they are similar, you place 0. So after that, okay, you compare the next adjacent bit. So that is 1, 0. Are they similar or different? So they are different. So if they are different, okay, you write 1. So therefore, the equivalent of 110 in gray code is 101. And that's it. Okay, so thank you very much. So if you have further questions, you may now raise your questions on our chat box. So if you have your mic, you may raise your hand and ask your questions.